In this video, we are going to be talking about isomers and all the different types of isomers possible with our carbohydrate molecules. Isomers are any molecules that have the same chemical formula but are different molecules. We have these two molecules here which have the same number of carbons. These two molecules, we have an aldose, aldotriose, and a ketone triose. These have the same molecular formula, but they have different functional groups. So our aldose has 1, 2, 3 carbons. This one also has 3 carbons. They have the same number of hydrogens and the same number of oxygens. Functional group isomers are a type of constitutional isomer, meaning that the arrangement of the atoms is completely different between the two molecules. All carbohydrates except for dihydroxyacetone have at least one chiral center. Remember, to be chiral, you have to have 4 different groups bonded around your carbon atom. And so for this molecule, which is D-glyceraldehyde, it has 1, 2, 3, 4 different groups on it. And that makes that carbon in the center a chiral center. Anytime you have a chiral center, that means that you can do the mirror image of that molecule, and the mirror image of that molecule will not be superimposable on that molecule. These are enantiomers. Enantiomers are mirror images of each other that are not superimposable. That means that we cannot rotate them and sit them on top of each other where they all line up. These will not line up on top of one another no matter how hard we try to rotate them. But they are mirror images. So that means that this set are mirror images of each other. You can also tell by the name that they are enantiomers. So they will have the same name, different letters. This one is D-glyceraldehyde, and the mirror image of that is L-glyceraldehyde. So in order to tell that D and L notation, we have to look at our Fisher projection, and we look at the last chiral center. The last chiral center in each molecule will be the last cross in the Fisher projection. Not the last carbon, not that last carbon, this carbon, the last cross location. This very last carbon in the chain has 2 hydrogens in it, which means it's not chiral. And so we have to pick this one, that's the last chiral center in it. If the chiral center has the OH group on the left, then that makes it the L isomer. If that has the OH group on the right, then it's the D isomer. I thought you might enjoy this little meme. This is Samuel L. Jackson here, facing left, and Samuel D. Jackson on the right. And that image should go chiral because it's so funny. Because of the enzymes in our bodies, a lot of chemical reactions are regioselective, meaning they are particular to, like, reactions make one isomer preferentially. All the reactions require one isomer preferentially. And so pretty much all naturally occurring carbohydrates are of the D variety. And so the D isomer is the one that's naturally occurring. But this is D-glucose, our most common sugar, and you can see its OH is on the right. Its enantiomer would be L-glucose because they would have a mirror image. You can see that all of them are flipped. Not just the location of this, but all locations are flipped. So the mirror reflects not just that bottom one, but the whole molecule gets flipped in the mirror in order to make L-glucose. When you have multiple chiral centers like you do in your tetroses and pentoses and hexoses, then you have a lot more combinations possible than just mirror imaging the whole molecule. If you just flipped 1 or 2 carbons, you could make molecules that are not mirror images of each other and are not superimposable. That means that they are diastereomers. So the term diastereomer means isomers that are not mirror images of each other and they're not superimposable. A special subset of diastereomers are epimers. Epimers are diastereomers who only differ in the configuration of one chiral center. So for instance here, let's look at the difference between glucose and galactose. If I skim my eye down this side, I see that that has an OH on the right, that has an OH on the right, so that's the same. That's an H, that's an H. This is an OH, that's an OH. And this one's not chiral, so that doesn't even matter. It's this location that's flipped. So these two differ in just the orientation of one chiral center. That means that these are epimers. Which number epimer are they? That's 1, 2, 3, 4. So galactose is the C4 epimer of D-glucose. Go ahead and try to fill this in. Allose is the blank epimer of D-glucose. Let's find out together. We have OH, OH, and then those are also the same. It's this one that's flipped. So allose is the 1, 2, 3, C3 epimer of D-glucose. Let's practice our classification. Go ahead and pause the video and solve this one, and unpause the video when you're ready to check your answer. Let's see. This is an aldehyde. I know that because it's at carbon number 1 and it's a CHO. Now we have 1, 2, 3, 4, 5, 6. So it's an aldohexose. So let's cross out the 1s. that are not aldohexoses. And then we have to decide whether it's D or L. And so then we look at this location. That's on my left. And so this is an L aldohexose. You do not need to memorize all of the different trioses, tetroses, pentoses, and hexoses. On Canvas, there is a reference sheet which you can print off and use when you're doing your homework and use on your exam. You are not expected to memorize the orientations of all of these different sugars. However, if you want to, this figure is very nice and handy for memorizing that sort of thing. And so here we have our one chiral center, and you can see that they keep that same chiral center and just insert one up above in either with the OH on the right or on the left. And so as you go down, they're always just inserting one OH group, which is highlighted purple in the figure. And then you can see that for each possibility, as you add one more carbon, you're doubling the number of isomers possible. Here's the same sort of figure with the ketoses. Ketoses, remember, they start with the ketone at carbon number 2, and so the tetrose is the first one that has the chiral center, and then after that, then the number of possibilities goes up double each time.